Hi math students, it's Mrs. Marcellus in for Cott. Today we're going to learn about functions and equations. Today's learning objective: students will solve algebraic functions by constructing and analyzing verbal, tabular, and graphical representations. Today's vocabulary word is linear function. A linear function is a function whose graph is a line. That makes a lot of sense, doesn't it, for Cott? The word linear has the word line right in it. When we're graphing linear functions, it's handy to note that our input-output tables translate into our x and y coordinates. This gives us the ordered pairs that we will need to graph a function. Then let's tackle the first problem. Let's write an equation to represent the function. When we're writing equations, we know that they're going to have an equal sign because an equation is a sentence stating that two expressions are equal. When we write algebraic equations to represent functions, we usually start with y equals. The output equals something that happens to x. We will analyze our table to figure out the rule. To get from 10 to 7, we are going to be subtracting 3. To get from 11 to 8, we will also subtract 3, 12 to 9, subtract 3, 13 to 10, and 14 to 11. Each time we'll put a value in for x and subtract 3 from it. So the equation to represent the function is y equals x minus 3. Let's write an equation to represent the function for this table. We'll start with y equals, and then we have to figure out what is happening to x each time. To get from 2 to 14, we are either multiplying by 7 or adding 12. To get from 3 to 19, we cannot multiply by 7 because that'd be 21, and we cannot add 12 because that would be 15. When we have a table where adding, subtracting, multiplying, or dividing by the same value each time will not give us the outputs that are in the table, that is a big clue that we're going to have a two-part rule. First, we are going to multiply or divide the x value by something, and then we are going to add or subtract. The first thing we want to find out is what is the coefficient of x. In order to do that, we will analyze our outputs. If we look at our outputs for y, we can see that to get from 14 to 19, we add 5. And this holds true from 19 to 24, and from 24 to 29, and 29 to 34. That means that 5 is going to be our coefficient of x. In our rule, we will have 5 times x, and then we will either add or subtract from there. If we take 2 times 5, we get 10, and then if we add 4 more, we get 14. So it looks like our rule is going to be 5x plus 4, but we need to check additional values to make sure that holds true. 3 times 5 is 15, and then if we add 4 to that, we get 19, so that checks out. 5 times 4 is 20, and if we add 4 more, we get 24, check. 5 times 5 is 25, plus 4 more is 29, check. And 6 times 5 is 30, plus 4 more is 34. So our rule is 5x plus 4. Next, let's try graphing an equation. In order to graph this equation, I'm going to create a simple input-output table. Then I'm going to choose some values to plug in for x and figure out what I get out for y. You might be wondering to yourself, what should I use as inputs and how many points do I need? When we have a function, you want to graph a minimum of 2 points. 2 points will form a line. However, if you use only 2 points and connect them, and there's a mistake in one of those 2 points, your graph is going to be completely incorrect. If you use 3 or 4 points, then you can see clearly whether or not they are lining up properly. You also want to take a look at the graph that you're given to work with. In this case, our graph goes only up to 8, so we want to make sure that we pick points that will fit on the graph. Usually it's a good idea to stay around the origin and pick inputs such as 0, 1, 2, and 3 for x. My outputs will be 0 plus 3, which is 3, 1 plus 3, which is 4, 2 plus 3 is 5, and 3 plus 3 is 6. Now I can go ahead and graph those points on the coordinate grid. My x and y form the ordered pair. So my first ordered pair to graph is 0, 3. I'm not going to write those all down, but I think you could see if I just added some parentheses to the table, we would have all of our ordered pairs. I'll start with 0 on the x-axis and go up to 3 and draw a point. Then I'll do 1, 4, and 2, 5, and 3, 6. Y equals x plus 3 is an example of a linear equation. If I were to connect these dots, they would in fact form a line. However, these are not the only values I could graph. For example, if I would have put 1/2 into the equation, I would end up with 1/2 and 3.5, which I'm going to go ahead and add to my graph. If I had added 4 and 1/4, and added 3 to that, I'd have 7 and 1/4, which I also will go ahead and add to my graph. In fact, there are an infinite number of points that you could graph. We also could graph negative values as well. So when we graph a linear equation, we usually will take the final step of connecting the dots. We also will put an arrow at both ends to show that this goes on to infinity. Let's try graphing 3x minus 2. First, I'm going to create an xy chart. Then I will plug in some values for x to find my ordered pairs. I'm going to start with 1, 2, 3 as my inputs. My outputs are going to be 3 times 1 is 3, then minus 2 gives me 1. 2 times 3 is 6, minus 2 gives me 4. 3 times 3 is 9, minus 2 gives me 7. Then I'm going to go ahead and graph those points. I'll start with 1, 1, followed by 2, 4, then 3, 7. Now to finish my graph, I will connect the dots. And I do want to be sure to put an arrow at each end to indicate that this graph does go on to infinity in both directions. The table shows the years in relation to the average weight in pounds of a leopard. Make a function table for the input-output values. Then write an equation to represent the function. The first thing we're told to do is make a function table, so I'm going to draw that. We can see from our graph that the x-axis has the years on it, and the years 1, 2, 3, and 4 are included, so I will add those to my function table. Then the y-axis is the pounds. In year 1, we have 20. In year 2, it's 25. Year 3 is 30. And year 4 is 35. Next, I need to write an equation to represent this function. Since it's an equation, I know that I'm going to have y equals something happening to x. I can get from 1 to 20 by multiplying by 20 or adding 19, but it doesn't look like that's going to hold true for the rest of the table. That's the big clue that I'm going to have a two-part function here. In order to find what I will multiply times x, I will need to analyze the output values. To get from 20 to 25, and 25 to 30, and 30 to 35, we are adding 5 each time. I'm going to have 5 times x, and since it's a larger value, it looks like I'm going to be adding something. 5 times 1 is 5, plus 15 will give me 20. 2 times 5 is 10, plus 15 is 25. 3 times 5 is 15, plus 15 is 30. And 4 times 5 is 20, plus 15 is 35. So I think it's safe to say that is our rule. It looks like the leopard probably weighed 15 pounds at birth and then gained 5 pounds each year. Well, Furqat, I'm sure glad that you didn't weigh 15 pounds at birth and then gain 5 pounds each year. It'd be really, really hard to hold you up here to do these videos, wouldn't it? Well, math students, this does conclude our lesson on functions and equations, so we're going to say bye for now.